Hey, in this lesson, I'm going to show you how to simplify rational functions, find x-intercepts, vertical asymptotes, and holes. So before you can find any x-intercepts, vertical asymptotes, or holes, you have to first simplify the rational function. So I'm going to show you how to simplify, and then I'm going to show you how to find those three things. All of these three things are associated with, well, the vertical asymptotes and the holes are associated with domain. So in my last video, we talked about finding the domain, and I did start to talk about vertical asymptotes, but we're going to introduce something a little new today. It's called a hole, but it's still associated with the domain. So vertical asymptotes and holes are both associated with domain because they're both talking about x. And then this isn't associated with domain, but we are also going to talk about x-intercepts. So today is all about x. There are such things as horizontal asymptotes. We're not going to get into that for this lesson, but it is a possibility. But again, we're just focusing on x today. So to simplify a rational function, you are going to have to know how to factor. So if you hate factoring, I'm so sorry. You're going to have to do it again. If you need to brush up on your factoring, you can go back and watch some videos of that. But we are definitely going to factor today. All of these should be pretty easily factored. I tried to pick problems that were pretty straightforward. So we're going to have to factor the numerator and denominator. Any factors that divide or simplify to 1 are going to show you where the holes are, and the denominator, anything that's left over in the denominator, is going to show you where your vertical asymptotes are. So when I talk about a hole, I keep saying hole, but I haven't even really introduced that. So sometimes in the graph, when you have a factor that divides out, or divides to 1, sorry, this creates a hole in the graph. And sometimes on a graph in the calculator, it doesn't really show up as a hole. But if you were to draw it by hand, you would literally put like an open circle in the graph where the hole is. So we are able to find the y value of a hole so that if you were drawing it on a graph yourself, you would be able to know where that is. Today, we're just going to focus on the x value of the hole. So first example, I have a rational function, and I wrote it this way because I wanted to kind of talk about that with rational functions. A rational function is a ratio of two different functions. So my two functions are f of x and g of x, and they're written as a ratio, so as a fraction, a rational number. I've got this 2 out front. It's not really going to affect my asymptotes or holes. It would affect the, horizontal asymptote, but vertical, not so much. So right now, we're just going to focus on factoring the numerator and the denominator. So I have h of x equals, of the 2 out front, and then x squared plus 9x plus 18. I'm looking for factors of 18 that add to 9. That's going to be x plus 6 and x plus 3. And then in the denominator, I'm looking for factors of negative 18 that add to positive 3. I think that's going to be 6 and 3 again. Let me check and make sure. 1 and 18, 2 and 9, 3 and 6. That's all. So yeah, it has to be a positive 6 and a negative 3. So in this function, if I were to simplify it completely, I have an x plus 6 in the top and in the bottom. This creates I'm actually going to use highlighter, hole in the function. Normally, I would use a pencil and mark it out, but I want to be able to see it. So there is a hole at x plus 6 equals 0. And then solve, and I get negative 6. So I have a hole at negative 6. X equals negative 6. Now, I'm not going to do it in this video, but if you wanted to find the y value y value of the whole, you would take -6 and plug it into what's left over. Don't forget the 2 out front. And then evaluate the function at -6 with what's left over, and that's the y value. But we're just talking about x today, so I'm going to go on. Now, the factor that is remaining in the denominator is your vertical asymptote. So this is the whole, and that's the vertical asymptote. So we have a vertical asymptote at x minus 3 equals 0. Add the 3, and we get +3 for a vertical asymptote. So I have 2 very important pieces of information here. I have a vertical asymptote, I have a whole, and then the simplified version of this would be h of x equals 2 times x plus 3 over x minus 3. So if your goal was to just simplify the rational function, that would be the simplified version. If your goal is to find the wholes and the asymptotes, then those would be those -6 and +3. If you're looking for the domain, I didn't ask for the domain, but if you are looking for the domain, I talked about that in the last video, so I'm going to go through that. It goes -infinity to -6, union -6 to 3, union 3 to infinity. So that's all that is has to do with the domain. I went ahead and put this in y equals of the calculator because I wanted to show you something. When you put this in the calculator, you want to use the original function because the original function is going to show that x plus 6 that's shared in the numerator denominator. If you just put in the simplified function, it's not going to show that whole. So you want to put in the original function. Now, if I go to the graph, I can definitely see that vertical asymptote at 3, but my calculator is not showing a whole at -6 like it should. So I'm going to go to the table. And definitely at 3, we can see that error. And at -6, there's also an error, but it didn't show up on the graph. So that's how you have to kind of be careful with calculators there. You can't rely completely on calculators, at least in this case, the graph, because it didn't even really show that. So doing it by hand and seeing that for yourself will show you what you need to see. Now I want to show you one more thing. For this example, I put in my simplified rational function. And what I want to show you here is what I was talking about earlier. If I pull up the graph, it's the red one. The red graph is my new graph, and it is completely overlaying my white graph, the original graph. So you can see that they are in fact equal. They are the same. But if I look at the table, the white one, y1 is the first graph, the unsimplified version, and y2, the red one, is the simplified version, the x plus 3 over x minus 3 multiplied by 2. So you can see in both that at 3, there is an error, which is correct. And then at -6, my original function does show that there is discontinuity, but my simplified function does not. So that's why you want to make sure and you put in your original function, because it's going to show you everything as far as the table. It's going to actually show that whole that is there, in fact, there. And then that new function doesn't show that because it simplifies out. So you do have to be very careful. Math is definitely a very tedious subject, and you have to pay attention to those details. And that's why it is important to know how to do these things by hand, because oftentimes technology fails us a little bit when it doesn't show that. I'm sure newer technology would show that, but if you have a good old trusty older calculator, it's probably not going to show that for you. So that's the first example. I want you to pause and try the second example. What we're doing here is we're identifying vertical asymptotes, wholes, and the domain. So we are looking for the domain. So go ahead and do everything that I did in that first example. Go ahead and do that for the second one. If you factored this one, you should have gotten x minus 9 times x minus 8 in the numerator, and then in the denominator, we have a difference of 2 squares. That factors into x plus 8, x minus 8. You can switch the order on those, that's fine, but those are the factors you should get. And then the x minus 8s divide to 1, simplify to 1, and that creates a hole in the graph. So where you slash out that factor, that's the factor that has the hole. And the x value associated with that factor is at 8. And then the factor remaining in the denominator is the vertical asymptote, and that is at x equals -8. So I have my hole, I have the asymptote, sorry, and then this is going to set up, I can't talk, our domain goes from -infinity to -8, union, -8 to 8, union, 8 to infinity. Again, I went through that pretty fast because in the last video, I talked about that in detail. So if you're confused on that, you might go back and watch that video. So there's the domain, vertical asymptote, and the hole. And the simplified, I didn't ask for this, but if that's what you're here for, the simplified rational function, why did I do h of x? That was weird. This is f, is x minus 9 over x plus 8. And if I were to graph those two functions, the graphs would be the same, but the second function wouldn't show that hole. So that's all you have to do for that one. All right, last one. Pause it, try it, come back. So this one, the numerator factors, it is a linear function, but it has the greatest common factor of 2. So you can pull that 2 out front and you're left with x minus 4. And then in the denominator, we have x squared minus 16. That's a difference of 2 squares, x plus 4, x minus 4. So the x minus 4s divide to 1. That creates a hole at x equals 4. And then the factor remaining in the denominator is the vertical asymptote, and that is at x equals -4. So that sets up my domain. I have discontinuity at -4 and +4, which creates 3 intervals. One that goes from -infinity to -4, union -4 to 4, union 4 to infinity. And then that creates our simplified rational function of g of x equals 2 over x plus 4. Now, I mentioned earlier, I'm going to mention it again just in case you're here for that. If you're looking for the y value of the hole, you would take 4 and plug it in right here, and you would get 2 over 8, which is a fourth. So the point, the coordinate of the hole, usually they just ask for the x value, but if you're drawing it on a graph, you kind of need to know where the y value is. And so that's why you would plug in that 4 and you would get a fourth. 2/8 was a fourth there. 2 over 4 plus 4, which was 2/8, which simplifies to a fourth. So that will be the coordinate of the hole, the point where the hole is. And that's all you have to do. Yeah, I did domain. So that's how you would do that one. Now, this isn't domain, but it does still have to do with x. So I wanted to throw it in here and talk about that. If you're looking for the x-intercept, so let's say you're needing to graph this or solve this problem, and to graph it, you need to know where it crosses the x-axis and the y-axis. We're not talking about y today, but if you're looking for the x-intercept, it is whatever factor is left over in the numerator. Whoops. Numerator. So when we were talking about domain, we look at the denominator, domain denominator, and when we're looking for x-intercepts, we look at the numerator. So in the examples above, you can take your simplified function and focus on the numerator. Or if you look at this part here where I did some scratch work, the factor left over in the numerator is the x-intercept, or the factor where the x-intercept is. So for this one, I think it was h of x. Yeah. H of x is 2 times, I was left with, actually, I'll just write the original, x plus 6, x plus 3, and this was x plus 6, x minus 3, and this factor is where your intercept is. I messed that up. So you can write it, you can say the x-intercept is at -3, or you can write that as -3, 0. It's a point. X-intercept is a point. So I want you to pause the video and try the next two. We've already done all the hard work. We've already factored it. We found the hole. So now we're just looking for x-intercepts. For the second one, f of x, I brought down that first one that I was working on, the kind of ugly one, but it shows everything. So the purple highlighter is where the hole was, the orange highlighter is where the vertical asymptote is, and the green highlighter is the factor left over in the numerator, which is the x-intercept. So x minus 9 equals 0 is associated with the x-intercept. Solve for x, we get 9. That's a point at 9, 0. So if I were to graph that, I would see that it crosses the x-axis at 9. The last one here, I didn't finish because I want to show you. When we simplified it, the only thing left over in the numerator was a 2. And 2 is not, it doesn't have a variable with it. So there's not really anything left over in the numerator. This indicates that there is not an x-intercept. And I'm going to pull up the graph to show you that, just to kind of confirm it. Because if you get to a point like this and you're like, I'm not sure, that doesn't make sense, just pull up a graph and take a look at it just to confirm it. So this is the graph of that. I have my asymptote at -4. I do have a hole at +4. It's not showing up here, but it is there. And then you can see that it doesn't cross the x-axis. Now here it looks like it's touching the x-axis, but if I really zoom in there, it's not. And it never will. Because there's a horizontal asymptote at y equals 0. I'm not talking about that in this video, but that's why. So it's not going to cross the x-axis there. So there's not an x-intercept. Now, if I pull up that previous example, this one, I'm going to type in the original function so that I don't mess it up, just in case I got any factoring wrong. X squared minus 17x. Type in your whole function, go to graph, and I'm saying that it crosses the x-axis at 9. And if I zoom in, this is a little bit ugly here. There we go. There we go. That's much better. Look at that. See how it crosses at 9? Like so nice and clean. That's an x-intercept at 9. I just love that. So if I look at the table of that, then I can see that at 9, the y value is 0. So I definitely can 100% confirm that there is an x-intercept there at 9. So that's the difference between those two examples there. All right, that is all I have for this lesson. I hope you enjoyed it. If you have any questions, please let me know. I'd be happy to help, and I will see you in the next one.